Dimensional analysis is often useful, especially in chemistry, where we will often look for things that are equivalent in quantity but might be expressed differently or might be looked at differently. A good example of this is converting to and from atoms and moles. For these more complicated dimensional analysis problems, we'll start with a single quantity, and then we'll use conversion rates to take this quantity and find its result or its equivalent. A good example of this is molar mass, where we look at a mole in terms of a set number of atoms. And so knowing the number of atoms can be very useful for a variety of chemistry applications. So if we start with 1 deciliter of water, we can actually use some dimensional analysis to figure out exactly how many atoms are in that deciliter. To do that, in this case, we know that our molar mass is in milliliters, so our first goal is to get these deciliters into milliliters. If you look on your formula sheet, you'll see that 10 deciliters is 1 liter. You will also see that 1 liter is 1,000 milliliters. We also know that the molar mass of water is that every mole is 18.01528 grams. We also know that the density of water is 1 gram per milliliter. So in this case, I want to replace milliliters with grams, so I'll position those oppositely. And we also see that the two actually turn out to be the same, which is a very handy specific design element of the metric system. And now that I have my grams, I can do my conversion. I'm just going to take 18.01528 grams and replace those with a mole. But again, despite the large numbers at play, the reason why we like moles so much, the reason why moles are so nice, is because they give us a set number of atoms. That number is called Avogadro's number, and what it says is that every mole is 6.022 times 10 to the 23rd power of atoms. It should be obvious by this point that our ultimate answer will be in scientific notation. Before we get too deep into that, let's make sure the units go away like they are supposed to, and you can see that they do. You can see that all of these divide out. And now what I'm going to do is just work around that. I'm going to save 10 to the 23rd for the very end, and then we'll just adjust as necessary to make sure that our final answer is in proper scientific notation. So again, I will divide by 10, multiply by 1,000. There's actually no need to do anything there. This is just saying that with water, a gram is a milliliter. That's not the case for every liquid, but it is the case for water. And then I'll just divide by 6.022. I'm going to deal with 10 to the 23rd later. If I carry out all of these operations on everything except for that 10 to the 23rd power there, I will get 33.427 times 10 to the 23rd atoms. But we have a small problem here, which is that that's not technically in scientific notation. To put it in scientific notation, I have to move the decimal point 1 place to the left. That's going to make that number smaller, so to counterbalance that, I'm going to make my exponent 1 bigger. Then I will get 3.3427 times 10 to the 24th atoms, which as you can see is a lot of atoms, even for something that's not very big like a deciliter. A deciliter is large, but it's not extremely large. And you can see, nevertheless, it has a lot of atoms in it. We can go the other way, looking at another substance, in this case ammonia, and here I will have 4.875 times 10 to the 20th power atoms. As you can undoubtedly tell, the scientific notation part can often be the most onerous part of these problems. To get around that, let's take care of the scientific notation part first, because everything after that will be relatively nice as these things go. So I am going to replace atoms with moles again. And again, to that end, we will use Avogadro's number. Again, the atoms divide out. And again, we're going to take these and subtract them. So I will get 4.875 divided by 6.022. That won't be a nice number, a nice clean number, but that's really okay. That's how science works sometimes. And we will get about 0.80953 times 10. And again, what we're going to do is take 20 and subtract 23, which means this is actually 10 to the negative 3rd power in moles. So not much of a mole, but that's what it is. And now what you can do if you want to, and I recommend you do this because it does make some things easier, is you can find 10 to the negative 3rd power, or you can convert this in standard notation. And to convert this to standard notation, we just move the decimal point 3 more places to the right. I get 0.000080953 moles. We then use the molar mass to convert this into grams. Every mole is 17.031 grams. We appear to be missing some information, though. We appear to be missing the density of ammonia. I've now corrected that oversight. We see that ammonia has a density of 0.73 kilograms per cubic meter. I have the ability to convert, but as you see, I'm going to need kilograms before I can do that. 1,000 grams is 1 kilogram. We also know that every cubic meter is equal to 0.73 kilograms of ammonia. And now we have this in volume. And then finally, we convert meters into centimeters. Well, we know that 1 meter is equal to 100 centimeters. But again, because we're dealing with cubic units, we have to cube everything. We have to cube all 4 of these things. And again, if we do that, we get 1 with 6 zeros, so 1 million. And now we should have everything we need to make this come out nicely. Don't forget that a cubic centimeter is the same thing as a milliliter, so when we're finished, we actually will have the milliliters that we need. And now, again, I multiply by this, divide by this, and then finally multiply by 1 million. And all of this will come out to about 18.89 cubic centimeters, and as we just said, 18.89 cubic centimeters is exactly the same thing as 18.89 milliliters.